Sea level rise is one of the most damaging consequences of climate change, and it's also one of the most difficult to predict. In this video, we'll see why that's the case, and in addition, I will make a suggestion as to how relatively good short-term, say 1, 2, or 3 decade predictions of sea level rise can be made. Just a quick reminder, I don't receive any outside funding for the preparation of these videos. If you find the video interesting, I'd appreciate it if you give it a like and maybe subscribe to my channel and share it with your friends. Geological data tells us that from the end of the last ice age, about 19,000 years ago, up until about 6,000 years ago, mean sea level rose relatively rapidly at a rate of about 1 meter per century, punctuated by 2 relatively sudden jumps of about 2.5 meters each. Then, about 6,000 years ago, the rate of sea level rise slowed down dramatically to only about 1 millimeter per year, or about 4 inches per century. However, around 1920, the rate of sea level rise began to accelerate because of increasing global temperatures. Much of the sea level data we have comes from tide gauges at nearshore locations around the world. These gauges continuously record the local sea level height relative to some fixed onshore height. Averaging those data over a 24-hour period yields the daily mean sea level for the location of the tide gauge. Starting in 1992, sea level data obtained from radar altimeters in Earth-orbiting satellites became available. These data are referenced to the precise knowledge of the satellite orbital height, so they yield very highly accurate measurements both of the mean sea level as well as detailed information about the variation in sea level over the surface of the oceans. Because tide gauges measure local sea level relative to a fixed local land height, the tide gauge data can be affected by isostatic rebound and by subsidence caused by onshore fluid removal. In addition, the tide gauge data is very spotty. For many parts of the planet, no tide gauge data is available. On the other hand, the satellite data is much more accurate, covers essentially all the ocean surface, and can show local variations from mean sea level caused by temperature variations, ocean currents, prevailing winds, and other factors. Unfortunately, only about 30 years of satellite sea level data is available. It's clear from the satellite data that there are significant variations in ocean height around the planet. The image on the left shows the results of measurements taken in 1993, while that on the right shows the results of measurements taken in 2017. Lower ocean heights are represented by the blue and purple colors, while higher ocean heights are represented in orange and red. From a comparison of the two images, the rise in mean sea level is apparent over the approximately 14-year period. Also apparent is the fact that in some areas, sea level is rising faster than in others. Large-scale weather patterns in the Pacific, such as El Niños, La Niñas, and the Pacific Decadal Oscillation contribute to local ocean temperatures, and thus to changes in sea level, making interpretation of the data somewhat challenging. However, a comparison of the earlier and later results for the Atlantic Ocean provide a good indication of the extent of the average sea level rise during this almost 14-year period. This graph shows 5 different estimates of mean sea level rise from 1900 through the present based on the available tide gauge data and compares it to the available satellite ocean height data. The 2019 reconstruction by Dangendorf et al., shown by the dark blue line, is thought to be the best estimate of sea level rise between 1900 and 1960. From about 1960 on, the various estimates converge as more reliable tide gauge data became available, and they all are in reasonably good agreement with the satellite data starting in the early 1990s. The key conclusions from this data is that the rate of sea level rise is accelerating, and that the rate of acceleration in sea level rise varies with time. This is what makes predicting future sea level rise so challenging. Increasing global temperatures contribute to sea level rise both from the thermal expansion of seawater as the ocean absorbs heat from the atmosphere, and from glacial ice melt and from ice sheet melt in Greenland and the Antarctic. Additional sea level rise comes mainly from changes in land water storage, mainly from pumping water for agricultural purposes. We have to remember that melting sea ice doesn't contribute to sea level rise. Several attempts have been made to model sea level rise over time. The charts show the results of 3 overlapping time periods. Increasing global temperatures contribute both to the sea level rise from thermal expansion and by melting glaciers and ice sheets over land areas. The models generally don't account completely for the observed sea level rise, but they come close. In addition to the factors causing gradual sea level rise, there also is concern among some scientists about the possibility of sudden events that could lead to episodes of rapid sea level rise. There is particular concern that the ice shelf associated with the Thwaites Glacier in the Antarctic is being melted by upwelling warm ocean water. If this ice shelf melts, it could allow a substantial amount of the glacier to slide into the ocean relatively quickly. That would raise the mean sea level by about a foot, a third of a meter, in a very short period of time. Climate scientists have attempted predictions of long-term sea level rise based on various representative concentration pathways, so-called RCPs. The RCP models include the impact of atmospheric concentrations of greenhouse gases such as CO2 and methane, and aerosols such as sulfate and soot from burning coal or emissions from volcanoes, along with the uncertainty in possible future emissions. Because of the long atmospheric residence time of the greenhouse gases, even if greenhouse gas emission reaches zero by the end of the 21st century, sea levels will continue to rise well beyond that. And as we can see from the chart, the uncertainties in these models are huge. Even if we were to reduce all CO2 emissions to zero by the end of the 21st century, we see that the sea level would continue to rise for at least 2 more centuries and maybe beyond. And it's even worse if all we can do is stabilize emissions by 2100. I don't think the high emissions scenario is realistic, but nevertheless, we can see that there's a substantial uncertainty in the amount of future sea level rise. While long-term predictions of sea level rise are very difficult to make, in my opinion, relatively good empirical short-range, that is, 2 or 3 decade local predictions are quite possible based on the existing tide gauge and satellite data. A least squares fit of a third-order polynomial to the existing recent data should be sufficient to capture the effects of the changing acceleration of the sea level rise caused by local conditions. Adding an additional foot of sea level rise to these estimates to cover the possibility of a sudden Thwaites Glacier event should provide a good basis for planners to begin to put in place measures to deal with the short-term threats from sea level rise. The effects of sea level rise, including sunny day flooding from astronomical high tides, beach and cliff erosion, and severe flooding associated with storms, already are being felt in low-lying coastal areas and island communities around the world. These effects are only going to worsen with time. The time for action to prepare for these events is now, and I think we have enough information to make at least short-range predictions of what the effects are going to be. Thanks for watching this video. If you have found it informative, please share it with friends and families. Also, please subscribe to my YouTube channel and give this video a like. Thank you very much.